Hello. We're going to do another problem that has to do with gravimetric analysis today. Um, I'm just going to read it, and then basically, once you've kind of done one gravimetric analysis problem, you've sort of done them all. But I also know that it can seem a little foreign when you're reading it, and so we'll do a few of them. And if you have questions, you can bring them into class and we'll, hash them out. But I think that this one, if you've already done the first one, should seem a little easier. And I would recommend actually trying to do the problem first before you go and kind of check what I'm doing. So I'm going to read the problem first. A teacher provided their students with an unknown alkaline earth metal, chloride, XCl2. So the reason that it's XCl2 is an alkaline earth metal is going to be in the second column of the periodic table, which means that it has two valence electrons. And as a metal, it forms a positive ion by losing those two valence electrons. And in losing the two, it can have that full valence shell, which is, going with the octet rule, very important to have that full valence shell. So the alkali metals, sodium and those guys, they're in the first column and they have one valence. And so they lose one electron and they are a +1. And then your alkaline earth, those are going to be a +2. And because they're losing two valence electrons. And then when you get to something like aluminum, that's going to be a +3 ion. The students dissolved the unknown sample in 50 milliliters of water. So again, when we dissolve an ionic compound in water, we're going to free up those ions. We're going to make it easy for them to react because an ionic compound separates, that really rigid crystal structure that's holding it together comes apart, and we're just dealing with free ions. The students added, using a burette, a known solution of sodium sulfate and measured the conductivity to know when the chemical reaction was complete. I'm not exactly sure how they are doing that, but as we go through, I looked for these problems. I got some of them off the internet, and they're okay, but this is a good time to tell you, you can't always trust what you find on the internet because I was thinking about them, and I don't agree with some of the answers that they came up with, and we'll talk about that, I think, when we get down to B. But I've never really heard of using a conductivity meter that way. Because it's going to be conductive, and then they're thinking one way about it, I'm thinking another, but we'll get to that. So at the completion of the chemical reaction, the students had 17.2 milliliters of 0.5 molar Na2SO4. The students then filtered, washed, dried to precipitate. Remember, when we filter it, it comes out of the water, and then we dry it, and if it's a hydrate, you can dry it over the Bunsen burner. If it's a precipitate, obviously, since it's on filter paper, you can't put it over a Bunsen burner. I suppose you could put it in a dish and then gently warm it that way, but generally when it's filter paper, you just leave it and let it evaporate. But they don't give us one of those tables. They're just telling us after we've, done everything, it's 1.579 grams. So when we're talking about sig figs, we're looking first at 50.0 milliliters of water. That's 3 because you've got a 5, which is a non-zero, significant, and then you've got that 0 to the right of the decimal. That shows that we looked in that spot, and so that's significant, and then the 0 in the middle is significant. 17.2, easy, that has 3 sig figs because you got 3 non-zeros. 0.50 molar that's molar concentration of the sodium sulfate. That's going to be 2 sig figs because you've got the 0.5 and then that 0, which is a final 0 to the right of the decimal. And then the 0 to the left, the 0 point, the one that's to the left of the decimal, that's not significant, that's a placeholder. And then 1.579, that is 4 sig figs because it's 4 non-zeros. So I'm going to go A through F here and just sort of jump down. Write a balanced net ionic chemical equation using X for the unknown. And so that's pretty easy to do. So there's my Na2SO4 and then XCl2. And the reason why it's Cl2 is, again, because that alkaline earth metal has 2 valence electrons, loses 2, becomes a +2, whereas the alkali metals only do 1, and then you got your chloride here as a halogen, and the halogens have 7 valence, they gain 1, and so all your halogens, fluorine, chlorine, bromine, iodine, all those guys are going to be negative ones. And so here you see it, all the ions I know that are there, that are reactants, I split them up. Now notice you put the 2 as a coefficient in front of the sodium and then the chloride right there because you need 2 of them to get the formula right. And so then I realize that, this goes also back to the last problem. Man, the sodium, that's going to be a spectator ion because everything with sodium is soluble in water. So I don't have to worry about that. And since the sodium's coming in with the sulfate and it was soluble, I know that my sodium is nothing I'm interested in. And then the chloride, same deal. I mean, NaCl, that's very soluble in water. That's not going to form a precipitate. And so those are my spectators. And a spectator doesn't take part in the actual reaction. So I'll actually, when we do this in class, you can cross them out like that. And we see that the sodium is the same on both sides, the chloride is the same on both sides, and that's why you cross them out. And so what's left is the alkaline earth metal ion, and then the sulfate, and then now look here, because that's a +2, that's a -2, that sulfate's a -2. It's just XSO4. Now, since sulfate is a polyatomic ion, you kind of just got to know it, but sulfate, pretty common. You'll know that by the time you need to. So I'm going to do B. As the sodium sulfate was being added to the unknown prior to the completion of the reaction, was the conductivity increasing, decreasing, remaining the same? So I think the conductivity is going to be increasing. And the reason why is, I'm going to read from my answer here. We're losing sulfate and the alkaline earth metal ions. So those are coming out of the solution. And they're forming a precipitate. And so obviously, they're not going to be contributing to conductivity. Because if you're a solid, if you are an ionic solid, you don't conduct electricity. And you could think about that, when you touch salt, table salt or something, or any ionic solid, baking soda, you don't get a shock. there's nothing charged in there, and there's nothing in like salt or any ionic compound that would conduct electricity. We need metals to conduct electricity. Um, so those are coming out of the solution and forming the solid. So those aren't contributing to the conductivity. But what we're adding is we're putting sodium sulfate in there. So even as we're losing the sulfate, we're losing the alkaline earth metal, we're adding 2 sodium ions. Um, so, um, you know, you say, well, but, you're adding 2, you're losing 2. But we've still got our chlorides in there. And so what we're doing is we're losing the alkaline earth, but we're replacing it on a 2-to-1 with sodiums. So for every 1 alkaline earth that comes out of solution with that sulfate, and the sulfate doesn't count because it wasn't there at the beginning, so that's a wash. So for every 1 alkaline earth, every 1 plus 2 metal ion that comes out of solution, we're adding 2 sodiums because sodium's a +1 because it's in the first column and it has a +1 charge. So we're adding 2 sodiums for every 1 alkaline earth that we lose. And so I think the conductivity is actually increasing. But, that's a long way to go. And you just got to realize that, if something falls out and forms a precipitate, it's not going to be conductive anymore. But we still have the chloride ions. They're not going anywhere. They're spectators, so they remain conductive. And then you've also, you're adding the sodium ions in there. So calculate the number of moles of Na2SO4 that was added by the completion of the reaction. I'm really glad they did this way, because for some reason, sometimes people get a little crazy with molarity and they don't like it, but it's an easy way to do the problem. So you got 17.2 milliliters. I got to switch it to liters because molarity is given 0.5 molar is 0.50 moles per liter. That big M means molarity here. And it's just moles per 1 liter. And so I've got half a mole per 1 liter. And I get 0.0086, okay? And I take my answer to 2 sig figs because right here I have 2 sig figs, here I have 3 sig figs. I'm going to keep the lesser amount of sig figs. So let's look at D. Determine the moles of precipitate was made. Ooh, that doesn't sound good. I'm going to fix that when I make my worksheet. Determine the moles of precipitate was made at the completion of the chemical reaction. So here's your stoichiometry step. And even though, again, it turns out same, you need to be able to provide evidence to actually set up the ratios so you can prove that that you start with reactants and you get to products. And so what I did here is that's how many moles of the sodium sulfate, and then there's 1 mole of sulfate, SO4, just take it all together, it's a polyatomic ion in 1 mole of sodium sulfate. So now I have isolated that sulfate ion, and you're going to see that that's really important as you go through a lot of these problems, is that you isolate that sulfate ion. And then in my new compound, that XSO4, I still have 1 mole of sulfate, which makes it really easy, which means I have the same amount of sulfate in Na2SO4 and the XSO4, which we would expect because we have 1 sulfate in both compounds. And then they just want me to calculate the molar mass of the precipitate and then identify the metal, which that seems challenging, but when you think about it, if we know that we have 0.0086 moles, the molar mass is 1 mole, so we're just cross multiplying. So they told me that my precipitate is 1.579 grams, and that is 0.0086 moles, grams per mole. And so in 1 mole is going to be X grams, crisscross, that's how I did it. And I get 183.6, which gives me the mass of 1 mole of my compound. I still think, I still have X there. And so what I'm doing to get rid of the X is I take that molar mass, I take away 1 sulfur, which you see here. I take away 4 oxygens, which you see here. That would be 64. And then I'm left with 87.53. And so I know that it's an alkaline earth metal. I know it's got to be in the second column of the periodic table. And that's really, that's the first thing you should think about, is it needs to be in that second column. And if you do that, you can just identify that pretty easily as strontium. Nothing else is close. And it's not perfect. But you got to realize that a lot of times in the lab, things aren't going to come out, exactly perfect. Sometimes on a problem they will, but you're shooting close. And the closest for us this time is strontium. Thanks for watching, and I'll have another one up soon.